So this is going to be like my last lecture, so if everyone else gets to do the heavy maths and I just tell you how to use this for fun startups. So yeah, question answering. Here's a bunch of questions. Like, when were the first pyramids built? Jean-Claude Juncker, that's a question, right? Like if you want to look this guy up in Google, that's what you would type in. Or then something like, how old is Keir Starmer? What's the current stock price for Apple? What's the weather like in London? Whom did Juncker meet with? When did he get to his lecture? Why do we yawn? These kind of questions. And so question answering is finding answers to that. So here's a bunch of answers. And like if you look at the questions and the answers, you can start to see that there's different types of questions, different types of answers. Something like, when were the first pyramids built, has a very easy answer, 2630 BC. That answer is never going to change. Jean-Claude Juncker, you get a definition of some sort. How old is Keir Starmer? 54 years. That number is going to change every year until he's dead. What's the current price for Apple? That was accurate when I wrote the slide. That's probably not even accurate anymore now. And what's the weather like in London? Again, that's something that will change constantly. Whom did Juncker meet with is something you can only answer when you know in what context I'm asking that question, because he tends to meet a lot of people. When did you get to this lecture depends really on who you are. So except for this guy up there, this isn't true, but you're 5 minutes late. And why do we yawn? Well, that's sort of some long explanation of why people currently think that people yawn. I looked this up on the train over here and actually realized that this is no longer what people consider to be true. Apparently it's something about cooling down the brain. It's got nothing to do with your blood oxygen levels. So there's debate on that. Anyway, questions, answers. So why do we care about question answering? For a whole lot of reasons, mostly because it's awesome. One really good thing about question answering is when you think about it, it's an AI complete problem. What I mean with an AI complete problem is that if we solve question answering, we also solve every other problem there is. If you have a magic machine that can answer all of your questions, you can phrase every other problem in a question and voila, you're done. But sort of less tongue-in-cheek, actually it is an AI complete problem also in the sense from an NLP perspective. If you sort of think about the hierarchy we think of in linguistics, you start with phonology and morphology lower down, and you move up to syntax and then semantics, then you go to discourse and pragmatics. In order to do question answering fully, you need to actually do all of these things. You can't stop at a syntax level. You can't stop at semantics. You have to understand discourse as well. You have to understand pragmatics. There are a lot of questions I will ask you where, so if without an understanding of the world, you won't be able to answer the question because there's a lot of implied understanding in there. Or, there'll be questions like, you ask me, should we meet tomorrow? And I'll say, I'll book a room at 4. There's sort of the implied answer in here that, yes, let's meet tomorrow at 4 o'clock. I'm setting up the meeting. But just from the word level, this isn't sort of obvious. Next reason why QA is awesome is that there's a ton of immediate and obvious applications for it. Starting with search, that's kind of a QA problem. Dialogue, information extraction, summarization. There's a whole lot of other problems in NLP that sort of fall out of question answering or can be viewed as question answering problems. And then of course there's a couple of really nice results we've already had. So I'm sure most of you will have seen sort of IBM Watson playing Jeopardy and winning at that. That's QA, and I thought that was really cool. And then there's other things like if you have an iPhone, Siri. If you don't have an iPhone, then probably Google Search or Bing or whatever else you may use for your search. All of these things have a component of question answering in them. And then the last reason, sort of from a research perspective, why QA is awesome is that there's tons of stuff left to do in it. We're really not that good at question answering yet, so there's plenty of interesting research and really hard problems, as well as, so if you want to do a PhD, for instance, loads of really low-hanging fruit, which is great, makes QA awesome. So let's get back to the questions from earlier. So what we actually care about in question answering is not so much the answer to the question, but how do we get to the answer? And so when you think of all of these questions, try to figure out how would you get the answer if you were asked that question and you don't already know it. And there's sort of myriad of different ways you can do that. So for the first question, when were the first pyramids built? Like 20 years ago, you probably would have sort of gone into into your home or your library and get the encyclopedia out and look it up in there. If you want to figure out who Juncker is, maybe you have a recent encyclopedia at home, or more realistically, so if you need something like Wikipedia, which is more up to date. How old is Keir Starmer? Now you need a really recent encyclopedia because probably 2 years ago nobody cared about him enough to put this into a big lexicon. So you need something more recent like Wikipedia again, and then to extrapolate how old he is, look at his date of birth and do the math. What's the current price for Apple? You need to get yourself access to a NASDAQ ticker, call up your bank, or turn on TV and wait till it sort of turns up in Bloomberg. What's the weather like in London? Well, we're in Oxford, so you kind of have to look at the Met Office or call up a friend who lives there, make them go outside and tell you. Whom did Juncker meet with? Well, that only makes sense if I give you context by saying, well, I'm talking about this one article I read in The Independent, then, well, you have to read the article and look it up there and sort of get the relevant quote from there. When did you get to this lecture? Well, that's personal observation. I'm standing here and I'm watching all of you, and maybe you remember yourself. And why do we yawn? Well, at that point, so if that gets really complicated, because you need to sort of now figure out, okay, who would actually research this kind of thing, find studies on the matter, find sort of the most convincing work, and then get an explanation from that. So this is kind of much more important, I think, when we think about question answering, sort of figuring out where do we get the answer from. And so what I'm kind of trying to get to is this, that like QA is really concerning itself with 3 different types of data. There's the question, there's the answer, and then in the middle part, sort of the context of the source, like the data set, the source of information that we use to extract answers from. And that sort of gives you sort of quite a good way of thinking about different QA tasks and how to design QA models when you sort of think about these 3 categories of data and trying to figure out exactly where does your problem fit along those 3 dimensions. So on the question side, you have simple factual questions, and in the literature, like they'll often be called factoid questions. That works in American English. In British English, it doesn't work because their factoid is actually wrong information. In American English, it's correct information. This is really confusing. So that's a simple question, like how old are you? Who's the sister of Justin Bieber? Whatnot. And there's sort of more complex or narrative questions, like what are the root causes that led to England voting for Brexit last year? That sort of gets a bit more complicated, right? Not something you can look up in a database. Then there's information retrieval style questions where you ask a question and you don't really want like a specific answer, but really what you want is sort of relevant documents or relevant bits of text, sort of pertinent to your sort of topic of need. And finally, there's library reference, which is I think kind of fun, but sort of slightly left field from the rest of these things. So this is when you don't have a question yet, but you know you have a question and you need someone else to help you formulate that question. So this is the kind of thing when you, like traditionally you would go into a library, you say, well, I want to write my master's thesis on something topic. And then the librarian will have to sort of help you figure out exactly how to narrow this down into something, give you the words you need to express your question, so if they will help you then start your information retrieval request. Now, on the context or source side, that's a bit simpler, right? The sort of easiest obvious thing is of a set of documents, just like a long corpus of documents that sort of contain all the information that you can extract your answers from. It could be something more specific, like just a single document, when you ask a question pertaining to one particular event, one particular article or whatnot. It could be knowledge base, so any sort of structured database of information. And then there's also tons of non-linguistic types of data, so something like GPS data, images, sensory data, stock tickers, whatnot. All of these things will again contain information that you may want to query. And so this kind of also then gives you an idea of the types of answers you can get, like just a single fact. How old is this guy? 54 years. An explanation, why did this happen? This happened because of this and that. A document, as in like showing me the Magna Carta. Here's the whole thing. Or the more elegant version, like a sentence or paragraph extracted from somewhere. Maybe you have a whole bunch of documents, they're all very long, and you really just want to have like one small highlighted paragraph from there. And it could be, an image or another type of object, like show me images of cats. That's a type of question answering. The answer is images of cats. Or it could be another question. So in the library reference sort of setup where you're like, well, I want to know about pyramids, then the question might be, do you mean like pyramids in Egypt, or do you mean pyramids in Mexico, or something different altogether? And so I think this is sort of going to be a common theme throughout the rest of the lecture, that whenever we talk about QA, that's sort of the first thing you should think about, like what's the question, where do I get the answer from, and what should the answer look like? Now there's a whole field of research in linguistics into possible taxonomies for questions. And it starts with the simple ones, what you learned in primary school, like questions are WH words, like why, what, how. For some reason, how is considered a WH word, who, what, when. Or it could be the subject of the question, like what are we after? Is it the name of a person? Is it a type of cat picture? It could be the form of the expected answer, like are we looking for a sentence? Are we looking for a document? Are we looking for a number? Are we looking for like a long, detailed explanation? And it could finally be sort of the types of sources from which the answer may be drawn, which goes back to the previous slide, as in where do we get the information from that we want to sort of use in our QA system. And so yeah, for the purposes of building a QA system, it's really useful to sort of start by ignoring the question and consider the sources an answer may be drawn from. So really, you always want to start by looking at the answer rather than the question, figuring out, okay, what are we trying to answer? Where do we get that information from? And then sort of all of the other pieces should fall into place. So yeah, I kind of said that just now, didn't I? 3 questions for building a QA system. What do the answers look like? Where can I get them from? And then the third question, what does my training data look like? So where you get the answers from is your source corpus. Like that's sort of the data that you use to get answers from. The training data is the whole thing of, well, we need something to help us learn a system that does question answering. Do we have like question and answer pairs? Do we have just a bunch of questions? Do we have none of that? Do we have some sort of user data? So when you think about something like how search works, in a lot of cases, like one really strong signal is click-through data, where you say, well, here's a question that someone typed in. What did that person click on afterwards? Oh, that must be relevant link to that that question. Let's maybe show that thing again next time someone asks a similar question. And yeah, so what I'm hoping is sort of that by the end of this lecture, by being able to answer these 3 questions, you should then also be able to build any sort of new QA system for any kind of task you can think of. That's a big promise, but let's see. So breaking this down a little bit more into sort of concrete areas of question answering that people do research on these days. There's something like reading comprehension, for instance, where the answer will be based on one document, and the context provided will again be a single document in most cases. So that's the kind of thing like in this article, what did Obama say? Or what happened with this car accident that I just read about? Then there's semantic parsing, which is interesting because here the answer that the system should provide is actually logical form, which you then possibly execute against the knowledge base, against some sort of database. And the context, so your source of all information, will be that database. So here the task is translating from language into logical form in such a way that you can then execute this logical form in a subsequent network. Then there's things like visual QA. So here the answer tends to be something quite simple and factual, and the context provided is one or multiple images. That's the kind of thing like how many cats are in this photo, 3. Information retrieval is also a type of question answering, where here now the answer is a document or paragraph or sentence or collection of these things. So every time you type in a search online, what's happening is information retrieval. So if your query is being treated as a question, and the answer you're given is 10 links. And now here the corpus is, well, the context is a corpus of documents. Like in the case of search, it'll be the whole web. And finally, there's library reference, which I mentioned earlier. So here, the answer, or more better, the answers, is sort of a set of follow-on questions from the person that you start this conversation with. And the context here is the structured knowledge available in the library of question and sort of the librarian's view on that knowledge. isn't the way that the librarian thinks about organizing that knowledge to help you narrow it down from 100,000 books to the 10 books you should actually take out that day and read. So yeah, that's sort of question answering from a sort of overview perspective. I'm going to talk about 4 of these types of question answering in a bit more detail now. So I'll start with semantic parsing, and then we talk about answer sentence selection, which is a form of information retrieval, just a bit more focused on slightly smaller data. And I'll talk about reading comprehension and visual QA. And again, like last time, just interrupt me if you have any questions. So, semantic parsing. Semantic parsing is the process of mapping natural language to a logical form. Whereas if this logical form should be formal representation of the meaning that you're trying to express in natural language. And depending on this chosen formalism, this logical representation will be something that you can execute against a structured knowledge base. So assume you have some database that contains information. You take a sentence, translate this into something that will look like a database query, run this in the database and pull out an answer, and then you sort of have a full end-to-end QA pipeline. An example would be something like this. So you have a question, how old is Kirstama? You translate this into some kind of pseudo lambda calculus. It's like, okay, we're interested in lambda x age x, so some age property or attribute of a variable. And then we further say x is a person, and the variable, so to identify that person, is its name, Kirstama. And then you can see how you can turn this into a SQL query, for instance. If you have like a SQL query, a database that stores people and date of birth, you could see how this would sort of allow you to have a really easy function that pulls out the date of that person, assuming it's in the database. And so here you sort of have these 3 steps going from question to logical form to the knowledge base query to the answer. And so semantic parsing is mostly the part of going from the question to the logical form. We kind of assume that the second part, once you have the logical form, querying the database is easy. In practice, that's actually really not easy most of the time. But let's just pretend it was easy for the purpose of today. So what do the knowledge bases for this kind of stuff look like? So typically, we represent knowledge in triple form. So it'll be something like that, like you have a married to relation, Michelle Obama, Barack Obama, or member of relation, United Kingdom, European Union. And generally, this is sort of relation, entity 1, entity 2. And you can sort of see how with these triples, you can store pretty much all kind of relational knowledge. And then you will have other triples, something like age of Michelle Obama, and then a variable, so not necessarily another entity in the knowledge base, but just a number. And the good thing is that there's several like really large databases freely available to use. So for instance, Freebase, I guess, was quite popular. That's actually defunct now as of last year, but that contains something like 1.9 billion triples of general knowledge, sort of all kinds of things about the world. Now that's been migrated into Google Knowledge Graph on one side, but also into Wikidata. And so Wikidata, I couldn't find the triple the relation number, but so this, for instance, contains information on 25 million entities. There's 25 million people and places and historical events that it has information on, and you'd assume you'd have a similar number of triples linking these things together and adding attributes to that. Something else that's really nice is OpenStreetMap. That gives you a couple of billion triples on geographic information. So landmarks, sites, streets, public transport, all of that. And then finally there's GeoQuery, which is tiny. In fact, it's 700 facts about US geography and 50 spelling mistakes. But it's really frequently used in semantic parsing work, so I figured I include it here for sake of completeness. And so the problem is now we have these huge knowledge bases, billions of triples of information, and they're really cheap because they're for free, and you've got loads of people editing them online and sort of making them rich and keeping them up to date. This is great. The problem is supervised data for semantic parsing is really expensive. So for instance, there's something like 3917. That's a standard data set that people use. That's 917 annotated questions with their logical form. That's nothing, right? That's tiny. Likewise, GeoQuery has some 880 questions on US geography, together with sort of a logical form and prologue. NL Maps, which is a bit bigger, was released last year, which is sort of a couple of thousand questions on sort of natural language questions on geography, linked with their representation in open maps. Now, the reason why there's so little data for this is that it's extremely expensive to annotate. Because you have this complex database schema, and now you need someone to take a natural language question and figure out how to express that in that schema. We can't do this with Amazon Turk, right? Because this is people you need to train up. So this is mostly like poor linguistics students in the US who don't have a stipend and sort of earn a couple of dollars on the side, learning these schemas and then annotating data for us. And trust me, that's really painful. So for instance, this is an example from NL Maps, like where kindergartens in Hamburg. This translates into something like query area key value name Hamburg something key value amenity kindergarten Q type lat long. You're not going to come up with that unless you actually spend hours looking at this database, and it will still take you time to write these things out quickly. That's why we have so little data on that.
Can you possibly do the other way really easily from the query back to some sort of free-form question like a handler?
I can't hold my hand over that, but it might be easier. And people are definitely looking at this kind of stuff. It's still not easy, as in, like you still want like a student under your supervision to do that rather than a Turker whom you pay 20 cents an hour. So yeah, you can. There's definitely ways to make this a bit faster, and there's a couple of groups in the US. So University of Colorado has this huge linguistic annotation project where they sort of churn out thousands of these things every year. But it's still a big effort. You need to train up all of these people, whichever way around you do that. All right, so loads of data in a knowledge base, not so much supervised data if we want to train these systems. So that's not ideal. Let's talk about it in a bit. But this is deep learning. So here's a deep learning approach to semantic parsing. And one really nice trick when you think about this is that we can view semantic parsing just as a machine translation problem. It's a sequence-to-sequence problem. You have an input sequence, natural language. You have an output target sequence, which is the logical form. And assuming we had data like machine translation, we can literally just use a system like that, put it in on the left side, spit it out on the right-hand side, and we're done. We know how to do all of this already, right? We can encode a sentence with a sequence model. We can decode it with standard mechanisms from MT. So just stick a decoder on it with a language model over the semantic parse. Maybe we can use some extra trickery from MT systems. The downside is that supervised training data is really hard to come by. And if you looked at MT systems that have trained with deep learning approaches, you need hundreds of thousands, if not millions, of data points to actually train something that is nice and general and reliable. We don't have that kind of data. Second thing is that depending on the formalism used, the target set is actually highly complex. So you might have a huge branching factor if you sort of think of something like Freebase. You try to make a hop like, what's the name of the high school that Barack Obama's wife went to? Then if you go from Barack Obama, wife of Michelle, high school of name, and at each of these points you have like 1,000 possible branches. Well, you have another 100,000 other relations that will immediately render your complete query useless, because you don't have any flexibility for error here. It's not like an MT system where if there's a couple of words that are not really in place, you still get the meaning on the other side. If this doesn't execute, it doesn't execute, and we're done. And then there's sort of other questions, like how do we deal with proper nouns and numbers, which again we can sort of take ideas from MT for, but obviously learning embeddings for all of these individual names is not going to be feasible with the kind of data we're talking about, where we have sort of billions of triples, but only training data in the thousands. So one way around this is sort of to just say, well, let's avoid logical forms in our data. And so when you think about how semantic parsing works outside of the deep learning approach, is actually quite frequently we come up with mechanisms, or people have come up with mechanisms that don't make use of the logical form, that treat the logical form as latent and just train on the question and the answer side. So I'm not going to go into this too much, but the idea is, for instance, in a standard semantic parser, you would sort of take your input sentence and then learn a parse on that. The same way you might learn sort of a syntax parse or dependency parse, we can learn a semantic parse. You can use some formalism like CCG, combinatorial categorical grammars, and you end up with this nice ungrounded graph here on the left-hand side, which sort of puts all of the words in your sentence into relation and can actually label these relations to some extent. And these we can train because we have sort of these nice formalisms developed in computational linguistics over the years, and we have tons of training data for that because this is just trained on natural language plus these formalisms which are sort of more rule-based, so they need less training data. And another trick is that people have been looking at for QA with the semantic parsing framework is to say, okay, well, we've got this ungrounded graph now that represents the question that we want to ask. Why don't we sort of just get a whole graph of sort of one of these triple databases and try to ground our graph by matching it onto there. So you come up with some heuristics of trying, for instance, to match names to the matching node in the semantic graph of your knowledge base and say, okay, well, I've got Obama here, I've got Obama here, so we can match these two. And I've got this dangling edge, which of the other edges going out of the knowledge graph can I attach this to, and so forth. So this kind of allows you to ground your graph in the knowledge-based representation. And thereby you can start learning from QA pairs rather than from question logical form pairs. So this is kind of nice. That's the sort of classic semantic parsing approach to that. It would be nice if we can do the same thing in deep learning land. And that's kind of what we're trying to do. So there's a couple of approaches we can sort of try to fight data sparsity and making these systems more robust, even when we use sort of a sequence-to-sequence style approach to that. So for starters, there's something like, just like an MT, we can use attention to make this thing a bit more robust, a bit more useful. And if we use something like pointer networks, you can actually pull out words on our source side and stick them into target side, which helps us speed up training again, helps us deal with something like proper nouns. The second thing is that we have this highly rigid structure on the target side, where if we're in a certain node in the knowledge base, then there's only so many relations coming out of that, and so we can constrain generation by saying, well, you can't generate anything right now. You have to generate one of these relations, so the space that you're trying to learn probabilities over becomes much smaller. And then finally, you can look at making use of semi-supervised data to counter sparsity. So we can say, well, it might be really expensive for us to generate question logical form pairs, but generating questions is easy. And generating random logical forms is really cheap because if we know what a database looks like, we can just write a really small script to spit out hundreds of thousands of logical forms that seem logical, seem plausible. We just don't know what the matching language for those is. If we can use semi-supervised training, we can then sort of train the system both ways and use sort of the bit of supervised data we have to make sure that, that sort of these unsupervised bits end up aligning as well. I won't get into too much detail for all of these, but I sort of put the 4 papers there that are sort of worth reading if you want to look into any of these things further. They're all actually really, really easy to read, I think, so that's worth doing. I'm on 2 of them, so I'm obviously massively biased in my choice of papers. So is Phil. One thing I want to talk a little bit more about was this idea of generation from multiple sources. So when we talk about normal sequence-to-sequence models, you have sort of your input sentence. That's your source, you encode that, and then you generate from the representation you've learned by encoding your input. So this is kind of what that would look like, right? For a sentence like, where can I find Witties? Witties is in Berlin. Now, what we can actually say is, let's make this a little bit easier on ourselves. Let's add something like pointer networks. We say, okay, if I want to give the answer to that, I don't need to learn to memorize sort of like every name of every donut place in Berlin and the rest of the world. I just need to remember that the overall question has this particular shape, and I can pull out this one individual word. Sorry. Not sure what's happening to my voice. So pointer networks basically say when generating, instead of generating from the latent state I have in my decoder, I can also choose to generate by indexing a word on the source side and just copying that over. So this kind of makes it a lot easier to deal with things like numbers that you want to copy over or names that you want to copy over. In this example, I'm using text, but you can see how you could do the same thing when you go from text to logical form. The other thing you can do is database lookup, right? So you can say, well, instead of, in this case, you're spitting out the answer directly, I can look it up in a database. The same way that if we want to generate a logical form, I could say, well, now I know I have to generate some relation. Let's look up in a database the possible set of relations and spit out one of those, as opposed to trying to memorize what I can do at any time step. So I think that's a really nice trick for making generation a bit easier. And again, it's a paper from last year where all of this is explained quite nicely in the context of like actually teaching computers to play card games, but the idea is exactly the same. So yeah, that's sort of semantic parsing. So in summary, the great thing about semantic parsing is that by saying we generate a logical form rather than an answer, this makes our systems much more robust. Because what we have to learn is sort of permanent in time. What we're generating is sort of independent of the state of the world, and the answer is independent of the question in the parsing mechanism. So this is great because we can deal with rapidly changing information, because the question will always go to the same logical form, even if that logical form will give us a different answer depending on where we are in time. The downside is there's a constraint to things that we can query in a knowledge base, query in a given database schema. And you'll find really quickly that no single database is big enough to sort of answer all of the questions you would possibly want to ask. And finally, what I sort of try to focus here really on is training data is really hard to find. So you have to come up with loads of little mechanisms to sort of fighting this data sparsity and getting your systems to learn, even so you have very little supervised training data to rely on. So looking back at the questions that we started with earlier, something like, where were the pyramids built? We can answer that. That's sort of a typical semantic parsing question. The sentence is sort of easy. We can parse that, and any sort of sensible knowledge base will have an answer to that we can just pull out by having the age relation of the pyramid entity done. Something like Jean-Claude Juncker is a bit trickier, right? I mean, it'll be easy to figure out how to ground it in a knowledge base. Like we just say, okay, look up this person. But then we have a node in knowledge base. We can then sort of build something on top of that says, okay, if this is all we have, then spit out all of the information we have related to this guy, and this may be what you're looking for. This may not be. How old is Kirstama? Again, easy. That's kind of pretty much the same logical form as we would get for the pyramids. What's the stock price for Apple? This again is something great with semantic parsing. Sort of easy, simple question, easy database query at the end. Likewise with the weather in London. Again, this seems like something where you can quite easily write a function that this translates into that we then query the appropriate knowledge base with. In that case, I guess the Met Office. Then, whom did Juncker meet with? We can't answer that. Right? There won't be a knowledge base that contains that information in the way that we're interested in it. I mean, there might be some document somewhere in Brussels that keeps track of everyone that he's ever met with, so the fullness of time. That's not what you're looking for here, so we can't answer that. When did you get here? Again, can't answer that. And why do we yawn? Any of these kind of explanatory questions, knowledge bases are not very useful for. So in balance, this looks good, right? Because we can answer 4.5 out of the 8 questions. There's one big caveat, right? That all of these questions here would require a different underlying knowledge base. While something like Freebase might be good for telling us when the first pyramids were built, because that's a bit like Wikipedia in terms of the information it contains, that won't give us the stock price for Apple. And then we might have some Nasdaq ticker that can give us the stock price for Apple. That can't give us the weather in London. So we can build nice specialized systems with that. It'll be very difficult to sort of come up with a nice general system that can answer all sorts of questions unless you go through sort of some meta process of first deciding which knowledge base to query, then querying the knowledge base and all of that, which computationally is just going to be really painful. So yeah, that's semantic parsing. Any questions at that point, or should we go into next?
So can you point any successful question answering systems built to answer questions like this and prove potentially?
Google search will do that to some extent. So when you search for something, and there's a little box at the top of your results which has an answer, there's a bunch of mechanisms going into it, but one of them will be a semantic parse applied to a knowledge base. So these things do exist. They just, they're quite fragile. And there was something like Google, it's fine because I guess then if we can't answer it like that, you get other types of results, other types of data in return. If this was the only thing you were relying on, then things get a lot trickier. They're pyramids, beautiful. So yeah, different type of question answering is reading comprehension. So this is basically the idea of answering a question related to a given document. And so this is, for instance, an example, right? If you have a question here that's a closed form question, like the driver was caught in the X, was a cutout of most interesting man, and you try to figure out what X is, you need to read the matching article to figure it out. And I sort of put an attention heat map over that, and sort of in that case, the system would actually figure out that this was the HOV lane. So in America, these sort of lanes where you have to have at least two people in a car in order to qualify for it. Someone decided to cut out this guy from the beer ad, stick the cutout next to him and go through that lane. He was caught. Pretty epic way to get caught by the police, I guess. So yeah, that's reading comprehension. And so here, there's a bunch of corpora. If you want to look at this as a QA problem, there's this corpus I just showed you, the picture from the CNN Daily Mail corpus, where you have over 1 million QA pairs with articles from either the CNN or Mail Online for context. And the target here is to sort of pick an entity from that article. So you have a question relating to an entity mentioned in that article. There's a children's book test corpus. It's kind of the same idea. Difference here is that for context, you're given a children's book or sort of a couple of pages of a children's book, and you have to answer a question about a person appearing in that book. And then recently there was this Stanford QA data set, which is doing a similar thing on Wikipedia articles. So here you have a whole Wikipedia article for context. And the questions actually look for something that is a span in the document. So it's not a single word, but it will be sort of a sequence of words in the document. All of these three corpora I'm sort of going to talk about now, that they make a couple of assumptions. So one assumption is that so if the context is read on the fly and unknown during the training phase, which is really important. So you can't train on your knowledge base because sort of your context will be provided with you to you at the same time as the question. And the second assumption is that sort of the answer is contained in that document, in that context, either as a single word or as a span. That constraint doesn't hold for reading comprehension in general. So you could also think of reading comprehension tasks where you're given a book or a document for context, but the answer is something that you have to extrapolate from that, where you have to sort of do some logical reasoning on the text to give an answer. The idea is just that all the information has to be contained in the context provided. And so yeah, this is sort of what these things look like in practice. So for instance, I'm from the CNN data set. There's this article about Jeremy Clarkson punching someone. And then the query is a closed-style query where we sort of take a sentence summarizing the article and drop out one person, one name, one entity. So this would be like producer X will not press charges against Jeremy Clarkson, his lawyer says. You have to figure out who X stands for just by reading the article. And so here it's Eusen-Thymann. And so actually for this data set, we made life a little bit easier by saying let's get rid of all of the proper names and nouns and replace them with anonymized entity markers. So actually what you get is something that looks like this. So all of the names have been now replaced with sort of these anonymous markers that are randomly permuted the whole time. And you still have to find sort of the marker corresponding to the correct answer. The good thing by doing this is sort of that it's quite easy to do that automatically on the fly with any new data you have. And by getting rid of all of the names, you can train a system on some articles that then also works for others, even if new people and new places are introduced there, because all of these will be anonymized. So now in order to answer this question, you sort of have to look at the context of the article. So you have to read the article and try to figure out basically just from that article what entity we're looking for, rather than being able to use any sort of external knowledge. So this sort of reading comprehension in its strictest form, because it doesn't allow you to use any external knowledge, even if you had access to it. And yeah, from a computational perspective, the nice thing with this anonymization is that this greatly reduces your vocabulary size as well, which means you can actually train these things in sort of reasonable time with reasonable memory without having access to crazy machinery. Sorry?
That's not manually?
No, we've got a million of these articles. That would be really hard. No, so you take a like a named entity recognizer. So you run a parser over your text, figure out what are all of the nouns, which of these co-refer, and then you replace all of these with entities sort of using a random process.
Did you always link them to coreference as a free step? Because I remember did you benchmark some coreference in the KBC?
Sorry?
Did you always pre-coreference the entities?
You have to. I mean, if you didn't, then they would just be random numbers that have no relation to each other. And then sort of the entity in the query, sort of the master entity, wouldn't have any match in the context, so you couldn't solve the problem.
Okay, did you have pronouns too, or did it have to be?
No.
Okay.
No, I mean, like pronouns you should still be able to recover just by having these entities. I mean, there will be some degree of ambiguity introduced by masking these things out, but that's sort of within the margin of error. So yeah. So let's assume you have this kind of a data set. So going back to sort of how we think about Q&A, that this is kind of easy, right? So we have the question, we know what they look like, we know exactly what our corpus looks like, is sort of this sort of short article of text, and you know what the answer looks like. It's one word taken from that context. So then it's really easy to come up with a neural model for reading comprehension based on that. And basically, what we want to get is the probability of the answer given a document and the question. And we can make this discriminative or generative because we know, well, the answer is contained in the context. So we can just classify over all of the words in that context and figure out which one is the most likely answer. And then the formula for that, I guess, the probability of that was proportional to some product of a representation of the answer. So this is WA here, and some representation of the query and the document. So that's this function G over both the query and the document. And, well, this is week 7 of the course, so by now you should be able to fill out all of the details. So the first thing we need to do is encode the question and the context. We use sequence models for that, that's easy. Then you want to combine, sort of Q, the question representation, and C, the context representation. That should be D, sorry. And you can combine them using an MLP, where you feed these two things together using some linear transforms and nonlinearities, or you can use something like attention.
So when you change the name for the labels or the placeholders, did you keep track of some gender, the gender of the name, or?
No, so actually they were permuted at every time you would see this document, you have different placeholders in different slots. So the idea was that by anonymizing them, you take all of the semantics out of that word. So you can only answer the question by looking at the context that sort of an entity marker appears in, but you can't make any assumptions about the marker itself.
Doesn't that introduce an ambiguity in some cases?
Yes. Yeah, that's fine. I mean, there's sort of like 5%, 7% ambiguity in the overall data set. But, you know, because it's the same ambiguity across everyone doing the task, that's sort of acceptable. So yeah, for the model, encode question, context using sequence model, combine them somehow using MLP, or use something like attention, which I think Chris talked about last week. And then once you have that, you have this joint representation, G of Q comma D. Now you can just say, well, let's select the answer using the attention heat map, like figuring out which word do we think is the most important for that query. Or we can say, well, let's use that representation as a classifier over all of the words we have. Or let's use this to condition a generative model to then generate the answer. The choice is really yours. But this is a really simple model, right? Now the questions are still, how do we deal with out of vocabulary terms? How do we deal with proper nouns and numbers? And actually, like in the context of this data set I just talked about, these questions are sort of solved for you because all of the proper nouns have been taken out. If they do remain inside, then you want to sort of revisit something like the pointer networks I talked about earlier, where you say, actually, for generating, we sort of don't generate a word from the vocabulary, but we choose an index from the context. So I don't need to have an embedding for a particular word. I just need to know where it appeared in the document. So this is, again, what the model would vaguely look like with a much smaller text. So we have something like, say, our context was Mary went to England. So we run, in this case, a bidirectional LSTM over that and encode that. Then we have our question, X visited England, who visited England? We encode that, we get this representation U. Now we calculate this attention vector between U and all of our context representations, and we get this value R, which is sort of the reweighted representation of the context document given the query. You combine these two again, and you get an overall representation of the query context pair, and you go from there. So this is really like a very simple model, and like by now I think in TensorFlow or NewTorch you could probably do this in 15 lines of code if you ignore all of the data loading. And that's pretty much how you can solve reading comprehension. A bit of math because I wasn't sure. Have you done attention? Should I skip this, or do you want me to go through that? No, nobody's going to say skip it because that's, no. Okay, let's just go through it quickly. So this is kind of the math for the previous slide. So assume you have some LSTM or some sequential encoder that gives you a representation y of t, in this case a forward and a backward one. Then we get a representation u, which is the concatenation of sort of the encoder y q, gone forward over q till the end of the question, and gone backward to the start in the reverse case. So this is just a bidirectional LSTM representation of the question. And we can do the same thing with our document, but now we index the representation at the document on every single token in the document. So we sort of take the forward LSTM up until that word, and we take the backward one from the end until that word. We sort of take the concatenation of that representation to get a representation of the document at every time step. And then what you do is you calculate the attention weights by combining these. So we take the query representation and combine it with every single one of the context representations to get sort of an idea of how similar are these, how relevant are these to each other. Once we have that, then we can softmax over these similarities, which basically gives us a vector of the length of the context document, judging how important every of these slots is for our overall understanding of the document in the context of the query. Right, so if I have this short document, Mary went to England, and I have my question encoding, going to look like, okay, how similar is this question encoding to what I have at Mary went to in England? So I get these 4 numbers, and then I use these to decide how to combine my LSTM outputs on the context side into an overall representation of the document. So this is what R is. And then all I do at the end now is combine it again with the question representation so that it's represented in its own right and not just as sort of the attention guiding variable. This gives you sort of this G of D, Q, and that's all you need, right? Because now I've got one vector representing the document plus the question that I can then just use to classify all of the potential answers, and you're done with sort of your QA system. Good. This is what it looks like in practice. So these things, just as more so in case you end up implementing one of these as part of the practicals or your exam or whatnot, they tend to take a long time to do anything. So for a long time, they will just randomly guess an answer and nothing will happen. And at some point, sort of training will pick up and then it will go reasonably fast that you go from 0 accuracy to reasonably high accuracies. This was a Google project, so this was trained on 25 GPUs in parallel, and I actually had 100 training runs of these in parallel. You probably don't have these resources here, but you can do this with a lot less code if you just write slightly nicer code than I do. All right, so one way to speed this up and to simplify this is sort of this idea of, there was a paper last year, attention some readers, where we say, well, instead of trying to figure out how to get this representation of question and document and then generating an answer from that, why don't we simplify it and just say, well, we know the answer is in the document, so we just get a question representation, and then we get a dot product of that with our context representation at every time point. So it is still a bit like attention. And then we just stop here and we say, well, so we get the probability of a particular index in our context being the answer. That's sort of just this product of the context representation and the question representation. And then if we want the word probability, the probability of a word being the answer, we just sum over all of the indices that contain that word. And you're done. So this is actually a really nice simplification of that, because it only adds the constraint that we assume the answer has to be in a document. That's a constraint we set in the beginning, so that's perfectly valid. And it will massively speed up training, because it sort of gets rid of a lot of the complexity later on in the model and has a much more direct gradient flow, direct information flow. So I think this is a nice model to look at if you want to think about reading comprehension.
Does that one have to go both directions, or was it just able to read one?
One direction is fine. Typically, if you have bidirectional encoders, you get something a bit more robust. I think I talked about this in text classification lecture. So it will slow down training. It's more memory intense and sort of more hardware intense, but you get something a bit more robust out of it over time. Cool. So that was reading comprehension. So again, pros and cons. The good thing is now we can ask questions in context, and a lot of questions that people ask will be in context. Like if you don't want to know about sort of general facts of the world, you will want to ask something about, oh, what did he talk about in that lecture? We have a context, right, the lecture slides. It's really easy to use these kind of models both in discriminative and in generative sense. Like to say, well, we want to classify over a set of candidate answers, or we want to generate an answer. It's quite easy to see how you could implement both of these. And the nice thing is we have large data sets available for that, large supervised data sets available for these kind of problems. The key downside, I guess, is that sort of this constraint on context is quite artificial in the sense that a lot of the times you will have a question that requires context, but you're not going to come up to someone and be like, hey, in this article, what's Obama doing there? You'll just read it yourself. So in a lot of cases, you will actually need someone to sort of both find the context and then answer the questions, which these kind of systems don't do for you. In terms of the questions from earlier, so something like, when were the pyramids built? Sure, we can answer that if the context is the Wikipedia article on pyramids. Jean-Claude Juncker, exactly the same thing. Give me the right context, we can answer that. How old is this guy? Yeah, probably can do that. What's the stock price for Apple? Well, I can sort of do that if the context you give me is the current NASDAQ ticker. More likely that's not the context you're giving me, so it's sort of like a maybe here. Same with the weather. Now things like whom did Juncker meet with, that's a more obvious reading comprehension style question, where you have like one particular context, say the newspaper of the day. And then more general questions like when did we get here? Why do we yawn? Obviously we can't answer with these kind of things that are designed to just throw out a single fact or a single bit of information. And again, here's sort of the caveat, I kind of mentioned it already going through the list. Like you have this need for context for all of these questions. And for some of these, sort of the context to provide is pretty artificial. Like if you want to know the stock price of Apple and you have the whole ticker list, you'll just look it up. You don't need a whole complicated AI system on top of that will find line 24 for you. So that's sort of what to bear in mind with reading comprehension. So we're 1 hour in. This would be a good point to have a break, or do you want to get over and done with it? Get on with it? Okay. Oh, it's really long, like an hour and something lectures. Fine. You've got more energy than I do. All right, so third of the 4 things I want to talk about was answer sentence selection. So answer sentence selection is a type of information retrieval. And the idea here is that we don't want to find a precise answer and give an answer, but what you want to do is sort of going from a big list of documents of possible answers, picking some sentences or some paragraphs that contain the answer to your question. So it's sort of a stepping stone towards question answering by saying, well, I don't know how to give you the answer, but I'm pretty sure if you read these 2 sentences, you can figure it out yourself. So there's an example from some search engine where you say, percentage of people who voted for Trump. It will come up with this paragraph. 26% of eligible voters voted for Trump, and so on. That's got all the information you need. This wasn't supposed to be bold. Like this thing that makes it bold, that's not answer sentence selection. That's probably something else, a bit more semantic parsing-like, or reading comprehension style-like. But if you imagine this wasn't bold, that's answer sentence selection in the real world. So here again, let's think about it sort of in terms of like QA paradigms. So the question you get is a factual question, possibly with some context provided. The data source is either the web, everything, or possibly the output of some information retrieval system. So quite frequently this would be something where you say, well, I have this whole list of, say, 100,000 scientific articles as my context. I have this question I want to ask. First I use an IR system to narrow it down to 10 articles, and then I use something like answer sentence selection to read all of these 10 articles and find the most pertinent paragraphs in there. And that's the answer, right? So one or several excerpts relevant to the answer, where the excerpt is sort of a sentence or a paragraph or something of that kind of length. Oh, no, this was, okay. And so here the answer now is guaranteed to be extracted. So whatever you spit out with an answer sentence selection system is something that is in the original context. Whereas in reading comprehension, this is something that you can generate or get out of the context. That's an important difference between these kind of approaches. So there's a couple of corpora again for this, if you want to play with that. So one that people have been using a lot is this track QA, track. It's a terrible name, which is of several hundred manually annotated question-answer pairs, where you have a question and then something sort of around 20 candidates to answer the question. So you have like a question and 20 paragraphs, and some of those will be marked as correct and the others as incorrect. And more recently, there was this Microsoft macro data set, which has 100,000 question-answer pairs, where for context you're given sort of 10 contextual passages. So this is very much like sort of what you think about in a search engine, where like if you search for something, you will get sort of your 10 first blue links, and think of those as your context for then the answer sentence selection system that tries to figure out, is there anything in those 10 pages that I want to move on top and show you, because that might sort of give you the answer without you having to dig deeper into the search. And likewise, sort of beyond these data sets, answer sentence selection sort of plays a role in information retrieval, like I said earlier. So anything where you have a large amount of data that you narrow down with some IR system and then narrow down further with a sentence selection system. And because of that, when you look at IR data sets or other types of QA data sets, it's quite easy to see how you can remodel a lot of them into something that will become a sentence selection style data set. So that there's plenty of training data out there for you if you want to work on this. A neural model for this, again, it's really quite straightforward, right? So basically what we need is a way to encode our question and a way to encode all of the candidate answers. And again, I'm not going to go into details for that. You've seen enough models for that. So take any sequence model or any sort of convolutional model to encode these things and give us a representation of our question and a representation of the answers. And now the only difference to bear in mind is that in something like reading comprehension or semantic parsing, when you want to sort of produce the next output, you have to classify one versus all of the others. You have to find the most probable output and output that. Whereas in something like answer sentence selection, actually, all sorts of answers could be correct. And you can return multiple answers. So here you have to classify each one of those individually by saying, is this relevant or is this irrelevant? In practice, what you then often have is sort of a second step of ranking these guys and just giving a single answer. But in terms of the actual task and the way that we evaluate this in machine learning is that actually you want to return a ranked list of everything and say which of these do we like, which are relevant, which are irrelevant. So yeah, one system for that is by Lei Yu, who's a PhD student here actually. So she came up with this system where you have sort of these bigram convolutions over the question and the answer candidates, and then a reasonably simple transformation where you map the question representation and the answer representation using the matrix transformation in the middle into one shared space, and use that to produce a signal whether something is a positive or negative answer candidate. That's nice because it's sort of like quite a clean system and quite easy to sort of see where it's going right and where it's going wrong, and straightforward to train. So this is a paper worth looking at. Now, as I said, so one difference is that now we have sort of several answers that could be correct, rather than just one correct answer. So we need sort of slightly different metrics to evaluate that. So the standard measure we could think of as accuracy, which is just a binary measure. So do we get the correct answer or not? And then the way to report that is obviously like finding the number of correct answers over the number of answers given, you have accuracy. What you do in answer sentence selection is often you report mean reciprocal rank. So what this does is basically you return all of your answer candidates ranked. And what this measures is effectively the position of the first relevant document in the list of things you return. So if you think of this sort of as an information retrieval measure, in search, like you search for cat pictures and you look, okay, the first thing is a dog, the second thing is a hippo, the third thing is a cat, then sort of that's the number that matters. And you stick this into the formula up here. So this would be 1/3 in that case if it's just one document. It would be a full one if the first picture was the correct one, and so forth. So it gives you a number between 0 and 1, basically gives you an idea of how far down the list you have to search until you get meaningful information when using a particular system. Another way to also evaluate these things is to look at a blue score. So this would be by measuring how similar the returned answer is with the answer candidates that you have and that you know are correct. And so you can use a blue score, which is literally just a machine translation measure for translation accuracy. It's kind of measuring bigram and unigram overlap between sort of your provided answer and the reference answers. The formula for that is really, really weird and complicated, and nobody actually knows it. We just all use the same Perl script to re-implement it. So I'm skipping over that here. But ask Phil if you want to know more details for that. Right? Awesome. Answer sentence selection, I was reasonably short. So what's the good thing about that? It's nice because it's designed to deal with large amounts of text, far larger amounts of text than we have in sort of reading comprehension style data sets, for instance. It's more robust than sort of true QA, if you so want, because it doesn't have to provide you an answer, it just has to give you sort of a relevant snippet of information. And so we can answer, in quotation marks, answer much harder questions. This requires some degree of logical reasoning. If we just have a system that figures out which passage is relevant, that's a far easier task when you think about it. And as I said earlier, there's sort of this obvious pipeline step that sentence selection fills between information retrieval and full-on question answering by saying, well, let's start with the web. Let's use an information retrieval system to narrow it down to 20 documents. And now let's use answer sentence selection to go from these 20 documents to 10 paragraphs. And then we have the 10 paragraphs that we can try to do any other form of inference over that requires, a semantic parse or requires something like reading comprehension, which might have more expensive models to run. The downside is kind of the same thing as the upside. It doesn't provide an answer. It only provides useful context for figuring out an answer. And so the real world use or usefulness of it depends on the underlying information retrieval pipeline. As in, I don't know what the English expression is for that. I think it's something like shit in, shit out. Like if you have an information retrieval system that gives you 20 documents that are completely relevant for your question, then, well, good luck finding relevant paragraphs in those 20 documents. So the system will only be as good as the pipeline feeding into it. That's much more polite. I should have checked that beforehand. Garbage in, garbage out. Awesome. Going back to the list of questions. So something like, when were the pyramids built? I think Phil actually verified that during the lecture. So that's something where answer sentence selection will give you a sentence that answers that question by providing some excerpt from Wikipedia. Jean-Claude Juncker, again, it will give you something sensible for that. How old is Keir Starmer? I kind of said no here, it could be a maybe. as in it will probably return some, some paragraphs or sentences relating to his age. The problem is, unless you build it more complicated, that's not answer sentence selection.
No,
That is knowledge base. If the problem is, it will return all sorts of sentences that say Kirstama, comma, some number, comma, some more text. And we don't know if this article is from today or from a year ago. So it will give you all sorts of different ages because it doesn't sort of have this temporal component in there. Likewise, the stock price for Apple, that's just going to randomly change, and you might get some article saying like, yay, Apple is at $100, and turns out that was from 2 years ago.
Are there any good data sets for training on things that change over time?
So coming in?
Are there any good data sets for training models where the answer might change over time?
I can't think of any directly. I mean, the most obvious thing would be any kind of semantic parsing type data set, because there, sort of what your model has to do doesn't change, even if the database that you look up the information in does change. Any other sort of databases models would be really hard, right? Because in a data set normally you get the questions as well as the context, and with the changing context, you need to convince someone to release a new version of the data set every day, and well, you're a PhD student, you know what that would be like. So yeah, what's the weather in London? Again, probably nothing useful we can get out of that. There'll be enough links to Lonely Planet telling you it's terrible, but maybe it's actually sunny on this particular day. Whom did Janka meet with is kind of the same thing, but again, here sort of the hope would be that if you provide more relevant context, we can do something sensible here. If say, this wasn't in web search where you have the whole web as your context, but using some sort of European Commission proceedings from a given day. When did you get here and why do we yawn? We really don't know how to answer these things. So again, that's a no. And yeah, as I said, so the important thing to note is that like a sentence selection system will probably give you answers for a lot of these kind of questions, but because the source will be static text that it will have pulled out of some information retrieval system, the information wouldn't be guaranteed to be up to date, which is sort of the implicit guarantee that you assume in a knowledge base. So that's it for text. So as the last thing I want to talk about today is visual question answering. And it's the idea that sometimes we have questions that require context outside of sort of pure language, and there's a lot of tasks for that. I mean, there's anything that requires GPS data, or when you want to look at sort of sensory data at home, but also there's visual question answering where you have for context an image or several images. This is an excerpt from some QA data set. What color are the eyes of that woman? I can't actually tell. Or what is her moustache made of? Bananas. These kind of questions that you always want to have answers to. And now the good thing is because this looks fun and this looks cute, there's actually been a lot of research in that recently, and people have produced massive data sets. So there's this visual QA data set from 2 years ago, and an updated version that was released a few months ago, VQA 2.0, and Coco QA. And all of these data sets have sort of hundreds of thousands of images, more than 1 million questions, and sort of millions of correct answers. So for a given question, you will have sort of many possibly correct answers. The details between these data sets kind of vary, but the organization is the same in the sense that you will have like an individual image paired with a question, paired with sort of a list of answer candidates, or maybe just a free-form answer where you have to generate the answer rather than classify over the possible answers. And now this looks fun. It's actually really straightforward when you think about it. So the question is language. We've covered that to death now. Just use any encoder to encode that question into a vector representation. The context is a single picture. So I mentioned convolutional networks a little bit in the classification lecture a few weeks back. So with convolutional networks, you can quite easily represent any given picture as a, again, compact vector representation that ideally holds most of the semantics of that image. And most of the time you wouldn't train these things from scratch, but you take sort of a fully trained convolutional network off of the web. There's actually, I think one of the most popular ones was built in Oxford a few years back, and stick that into your system. And seeing that the answer is a single word, well, we have a vector for the question, we have a vector for the context, find some way of combining these two, and then build a classifier to spit out your answer word. That's kind of all there is to it. Right? I mean, this is sort of what this looks like. So with the input image, we take our pre-trained convnet, we get our vector, we take our word embedding model. In this case, they didn't even bother running an LSTM over it. They literally just add together all of the different vectors, because the language tends to be so simple that having an additive sentence encoder works fine. You have some fully connected feed-forward neural network, which is a fancy word for an MLP in most cases, to give you a single vector representation, and then you classify over that. So in this case, the assumption is you have 1,000 possible answers, so you have a softmax over 1,000 dimensions, and you're done. Now, you will see I'm sort of biased a little bit against visual QA. So if you want to build a good QA model, the first thing you can do is throw away all of the images and just build just a language model as a reasonably strong baseline. So think of questions like what color is the cat, or how many chairs are around the table, or what's this big object in the bedroom, or where's this person sleeping. I don't need to show you the image that accompanies that question for you to give me a reasonably good stab at an answer. Like, how many people think the cat is black? How many think the cat is ginger? Who thinks the cat is purple? Exactly. Right, there's like 5 possible answers, so you have a 20% chance of getting it right. And if you assume there's 1,000 possible words allowed in your answer space, then actually your model starts to look really good if you bring it down to 1 in 5 choice. And so people have actually done this, sort of just ignoring the images, publishing papers on, like, I do visual question answering blindfolded, and did surprisingly well in that. So there's this Goyal et al. Paper from last year. So what they did afterwards was release a new question answering data set with images that was sort of designed to counter all of their techniques. So if you use something more recent, you may actually have to look at the images. Something else you can do, which is really nice, this is a paper by Xichao Yang from 2 years ago now, is so if you think of visual question answering using the default QA paradigm that we used so far in this lecture, then you'd see it kind of overlaps with reading comprehension a lot, right? We have sort of our small controlled context, we have the question, and we use some way of combining these two to give us an answer. And so something that really helps in reading comprehension was using attention. And we can do the same thing on the visual representations. Actually, attention visual representations is much cooler, because now it's not sort of just focusing on one word and the representation of that word in the context of a sentence, but it's focusing on some part of the image. And so there's this stacked attention networks for image Q&A paper from 2 years ago that did that. So you again have your language encoder and your CNN, like the convnet for encoding the image. And now you use that representation, as in the sentence representation, to attend to different sections of the image representation. And then you subsequently use that combined with this to spit out the actual answer you want to give. And we can visualize these things. And it's kind of, I think this is kind of pretty nice. Like something like, sort of the first example here, like, what are pulling a man on a wagon down a dirt road? And so if this is the input image, and then if you tend once, so if it's a focus in on the white areas, and then if you tend again, it really zooms in on these two things, which are the horses, which are also the answer that you're looking for. Or likewise, this kind of thing, like how many people are walking up the mountain. Like in the beginning, it's a little bit confused on where to tend, but then after a few steps, it will focus in on the people and be able to classify this correctly, giving you the right answer. So this is visual Q&A. If you see visual Q&A, think reading comprehension, and just replace the language encoder with a convnet, and afterwards all of the same tricks apply. But you get much more fun papers because, pictures. In summary, for visual Q&A, which was sort of the last thing for today, the nice thing is sort of you get this extra modality for free. Now you do question answering not only over text, but over text and images. There's a lot of training data available as of recently. The main downside is this is, like currently it's quite gimmicky still. I mean, most of the questions you will see that no sane person would ever want to ask. And it's still got a reasonably long way to go to be useful in real world settings. So when you think about like live applications of that in terms of helping the blind navigate in an urban environment, that sort of thing. In terms of the questions I had in the beginning, there was nothing with images, so I can't really answer any of those, except for possibly what the weather is like in London if you give it the appropriate picture. So yeah, that's visual question answering. And yeah, so in summary, I guess what I wanted to talk about today was sort of how to build your own QA system using all of the techniques you've learned in this course so far. And I think really the way to approach this is sort of to ask 7 questions, right? Like what is the task? What are you trying to solve for? And then what does your data look like? What kind of questions do you have? What kind of answers do you want? What does the context look like? What does the source look like that you get your information from? And now once you have this, where does the data come from? The training data, as in do we have supervised question answer pairs? Do we have supervised questions in logical forms? Do we have images and cat counts? And then can you augment the data? If you don't have a lot of data, can we find ways to augmenting the data? Can we generate new data cheaply? Can we add semi-supervised training because we can generate loads of data in one modality rather than the other? And once you've answered all of these data questions, then it's how do you encode the question in the context? And the standard answer will always be a sequence-to-sequence model or convnet. How do you combine these two things? Can we use attention? Does it make sense to merge them in some fun way, or do we just concatenate them? And once you have that, how do you predict or generate the answer? Which then depends on multiple answers. Possibly, do I have to sort of classify them all individually? Do I need to generate an answer because it's something longer? Is it something where I need to point back into indices of the context document because I want to return a span? Is it just a single word from a list that I can just classify over? And that's it. I think once you have sort of these questions, then you've got everything else that you need to build one of these systems. And as I said at the beginning, there's sort of this is an interesting topic in the sense that we're at really early days in terms of research there. So there's sort of plenty of open questions left. And I think just the important thing is to always start by looking at the data, looking at the answers rather than looking at the questions. That's it. So yeah, I skipped over a fair amount of detail for some of these things. This is sort of my view of sort of the most sensible, easy to read papers for the various sections that I talked about. So do have a look at those. And yeah, as always, if you have any questions, thanks.